And what I'm going to talk to you about today is something which is very close to my heart, is FRBs, fast radio burst. And I'll tell you what are things we have done in the last 3 to 4 years that have changed the scenario and made us be more aware of their origin. Now, very quickly, what are FRBs? So fast radio bursts, or FRBs, are extremely powerful radio emissions coming from cosmological distances, and they only last for a few thousandth of a second. But what makes them even more intriguing is the fact that an FRB arrives at Earth roughly every minute through different directions, making them one of the most prodigious and ubiquitous radio transients known today. And so if you have radio eyes, you would have seen FRBs like this. And so we have detected more than 1,000 FRBs, and a very small fraction of them actually repeats. We don't know whether these are different classes, but the question that that intrigues me the most is their origin, and we don't know it. Now, in my work so far, I have used a special set of FRBs which are detected in the local universe. And why? Because first of all, if you have the DM, which is the measure of the free electron density, then an FRB signal interacts with on its way from the source to us, and that tells us something about the distance. So when you have low DM, you can say that the contributions of other component, for example, Milky Way halo, Milky Way interstellar medium, intergalactic medium, and also the contribution of the host is not sufficiently large enough to make them place far away from us. So if you believe me right now, I can say that if the FRBs has dispersion measure excess less than 100 units, these are definitely in the local universe. Now, you may ask why these FRBs are special. Now, I'll tell you first thing is, I think most of you would agree that local universe candidates are the most promising sources if you want to identify their counterparts. So that's one thing. And second is, we can constrain the FRB luminosity function very well using these local universe FRBs, and especially if they're repeaters, which in my study I found that these are most likely to be repeating sources. And there are also interesting sources for FRB to constrain the Milky Way halo distribution, which is so far poorly understood. Now, I don't have much time, I only have roughly 5 to 6 minutes, so what I'll do is I'll discuss about something that I've been doing along with other stuff in last 2 to 3 years, which is identifying the host galaxies of these FRBs. In this study, I'll only discuss 3 sources. So if you want to know more, please contact me, and then there will be a paper coming up, which is a review kind of paper, where you will understand the contribution from this source. Now, the first FRB I want to discuss is FRB 2020-0120E. Now, what makes this FRB very special is the fact that the dispersion measure of this FRB is very small. It is in fact the smallest or the lowest DM FRB known to date. Now, just by looking at the DM, we can say that this FRB has to be in the local universe because the excess DM is very small. You cannot, even if this contribution is purely from the IGM, you cannot place it beyond, for example, 130 megaparsec. Now, this is how we detect FRBs. By the way, I don't know, for people who are not FRB aficionados or pulsar folks, we can estimate the dispersion measure by looking at the FRB spectrum, which is nothing but time versus frequency. Here we have corrected for the dispersion measure or for this DM value, and that's why you see it very sharp pulse on the top here. Now, so what I've done is I have looked at the host galaxy for this FRB, and I found that this FRB is localized here. Now, if you just look at the optical image, there is a kind of inflation that you have in mind that this FRB is out of nowhere. But when you actually look at the H1 data and other data sets, you really realize that this FRB there is an extended H1 disk that lies very close to the FRB, in fact, within the FRB localization region. And with other arguments in the paper, we made a very strong claim that this FRB is actually associated with M81, and hence the closest extragalactic FRB known to date. Now, I also listed some of the interesting possible counterparts, but because the localization region is not very good, we cannot actually say which one is exactly associated with this FRB. Now, so we collaborated with our friends in Europe, and we found that this FRB is actually associated with the source 3 that I've identified in the paper, and this is a globular cluster. Now, if you know anything about FRBs, the most promising model we claim for FRBs is young magnetars. Now, these are not the sites where you actually form such young magnetars, especially using the prompt channels like core collapse supernovae. So that presents currently the strongest evidence to date for the existence of multiple FRB formation channels. And there are many multi-wavelength follow-up analysis underway, and you will soon see a pile of papers coming up discussing different constraints. So stay tuned. Now the next, So the next FRB I want to discuss is FRB 2018-1038. Now the first FRB is localized to a globular cluster, but this FRB I found to be localized really to this NGC 3252, which is in our own supercluster. And that galaxy is located at a distance of 20 megaparsec, and which makes it the second closest FRB known today. We are still trying to find out the repeaters, but this source is highly non-Poisson, which adds another layer of complication in the properties of repeating FRBs. Now, but there are certain implications from this analysis. First of all, just by looking at the number of detections we made in a limited period of time, in a different sort of co-moving volume, you can see that the volumetric rate is so large that it cannot be sort of satisfied by the formation rates of compact sources like core collapse supernovae. So it means that these low luminosity FRBs, which are mostly the low DM FRBs that I've discussed so far in all of my papers, they are likely to be repeating sources, hence make them one of the most interesting sources for any sort of follow-up studies. And also, when you can see that by looking at the co-moving density, you can say that these FRBs are unlikely to be produced by young millisecond magnetars, one of the proposed model to produce these FRB sources. And we have currently the strongest constraint on the Milky Way halo DM contribution, or the amount of baryons there in that specific site line. I don't have time to discuss the whole, this is a whole new area in the FRB study. Unfortunately, I don't have time to talk about. But the one thing I definitely want you to understand is this phase space plot where x-axis is the duration and the y-axis is the energy. Now you see that FRBs, most of the FRBs lies here, and this is a galactic pulsar population. You can say far-flung brother and sisters of these FRBs. But then what you can see is these FRBs are actually bridging that gap between two apparently dissimilar population. And that's how we can actually test different emission and source models. Now, last but not least, this is the last source I see. So this is the first CHIME FRB we detected, and the crux of this story is this FRB we found that is most likely associated to an elliptical galaxy, a red-ended galaxy, where again you don't expect young stars to form. So the first detection to a globular cluster is not what he calls a winner's curse. There is still genuinely a possibility of the existence of multiple formation channel. So I'll end my talk with the summary slide, and hence we need more localizations definitely. But I end my slide with this presentation with the summary slide, and I'm very happy to take more questions if there is any. Thank you.
Hi Mohit, thanks for the talk. I was just wondering, your conclusion was that we need to look more at these host galaxies so that we understand more about them. So detections of FRBs in other wavelengths will be something that will be super helpful. I'm pretty sure about that. So what are your thoughts on the X-ray emissions of FRBs? Is that something that is possible given that extragalactic emissions? Not talking about the SGR flares that we have seen.
No, I was actually thinking you were somewhere at the Daksha point here, which you did. Amazing. Yeah, absolutely. So one thing is you really need to have multi-wavelength counterparts, because that's the best, one of the well-tested, historically tested way to understand the origins of, for example, gamma reverse. So we, and especially because last year, CHIME, we detected FR X-ray emissions coincident to the FRB-like emissions from a galactic magnetar. So there is X-ray coincidence there. So definitely this single evidence which should make you excited about possible X-ray counterparts. And hence, we are also doing that.
Anything extragalactic? I understand that the SR flare was something that was in the Milky Way, but
Do we expect a detectable signature that are coming from FRBs that are outside Milky Way?
True, true. So the point is, if you just look at the X-ray to radio ratio and assume that the emission mechanism is sort of self-similar. So if you increase the radio emission, you can also increase the X-ray emission. In that case, that galactic magnetar emission is actually not. It's one of the faintest. It's similar to the faintest FRBs we detected. So if you really increase it by, for example, 10 times or 100 times, we'll also increase X-ray by that. So we can actually increase your frontier to say 100 megaparsec to 150 megaparsec. So yeah, so there is absolutely +1 for a follow-ups.
A quick question.
Sure, please.
Just a naive question. What could be the physical origin for this FRB? Is there anything known about that?
Yeah, so from the discovery of FRB-like emissions from a known galactic magnetar, I think neutron stars are one of the most promising candidates right now, but we still don't know what are causing them.
Okay, great. We can continue further discussion later.